Welcome back. We continue to talk about properties of cathode rays, and in this section I want to talk about the fact that when cathode rays, which are fast moving electrons, enter a magnetic field, they are deflected. In fact, cathode rays are deflected by both electric and magnetic fields, but we want to study a little bit more about their deflection in magnetic fields. Before we do that, I'd like to go to the last simulation that I used, or rather the last diagram that I used. And in this diagram, I've indicated the particles which are deflected in this electric field. The negative sign, the particle with the negative sign is the electron, and you remember the electron is very light, while the particle with the positive sign is the proton, and it's heavy. So when we say that the proton is deflected less because of its mass, the deflection is this amount. You can see that this is much less than this arrow. So the reason why the proton is deflected less is because it is much heavier than the electron. However, the two are deflected in opposite directions because of their opposite charges. In this example, I'm using the electron and the proton as examples. We've got very many other charged particles out there. For example, let's assume we can have an ionized, a certain element in gas state, and then it is ionized, like sodium ions, for example, or chloride ions. They will be deflected the same way if we are able to accelerate it that way. So that's all I can say about this particular sketch. In the next sketch here, I have a magnetic field. This diagram here shows the electrons subjected to a magnetic field, and this magnetic field is into the paper. I want us to study that first, and then we can come back to this diagram. So let's head over to my second camera where we are going to study this situation, and then after that we will come back and conclude our lecture. So I've decided to use this simple model here. It's just a simple model that I've made out of cardboard. I have used a normal bulb, and this one is the plastic that holds the paper tape. So why am I using this? First of all, the bulb will represent the cathode ray tube. You see, the cathode ray tube is round like that, and the electrons are being produced at this point. I just want you to imagine that this represents the cathode ray tube, and we know that since it looks like the cathode ray tube, then the electrons are produced at this point here, and then they are accelerated. By the time they reach this point, they've got uniform speed, so they travel straight and they come and hit this part of the screen there. So when we say that we are talking about the deflection, we can turn it around like that, and then we can assume that actually we are looking at this as the amount of deflection that occurs. So when we don't have an electric field or a magnetic field, then the electrons will hit the center of this bulb at this point. Otherwise, when there is an electric field with the upper part being positive, the lower part being negative, then that spot jumps up or down. We have already looked at that. I want us now to think about a solenoid. A solenoid is a coil which is carrying current, and we know that a coil which is carrying current is actually a magnet. And then we get that solenoid, we split it at the center so that here there will be a continuous line. Now I'm talking about this part and this part. This part is made up of turns, very many turns of insulated wire. That wire will come to this other side here and continue in the same direction. And then the two ends of the wire will be connected to a battery. We are going to have a solenoid with a gap at the center. The reason why we want to create that gap at the center is so that the CRT can fit right inside here. But we are going to have magnetic field lines. Maybe let us say this side is the North Pole and this is the South Pole. North and South outside the solenoid. So magnetic field lines are going to start from here outside the solenoid, and they are going to move round like that, and they are going to enter the solenoid from this other side. So magnetic field lines will actually be moving from this side to this side inside the solenoid, but from this side to this side outside the solenoid. It is easier to see that when you imagine that you've got a loop which starts from here, moves outside, and then from the other side is going to move inside and then make contact here. Those magnetic field lines, the way they are moving, because they are moving from this side to this side, we can view this solenoid or this setup here from this side here. Once I view it from that side, then I will turn it around like that, so that at this time magnetic field lines will be moving into like that. So that is the exact situation that I have on my diagram. So let's go back to the diagram and continue studying that. So this is exactly what we've been able to see. So over here, this is the plane of the paper, and we have magnetic field lines moving into the paper, and the electrons are moving like that. A concept that I'd like you to appreciate at this point is, if electrons are moving that way, then electric current is moving in the opposite direction. Why am I bringing in electric current? I have charges moving in a magnetic field. When charges move, they constitute an electric current. It's more like the magnetic effect of an electric current. When we looked at the electric motor, we were looking at a current, a conductor which is carrying current, and that conductor is placed in a magnetic field. This time, the charges are not held in the conductor. The charges are in vacuum. They are free to move in any direction. They are not held by the boundaries of the conductor. But they still constitute an electric current. So, actually the electrons are moving this way, electric current will be moving in the opposite direction. So we have, let's go to Fleming's left-hand rule. We have, this is current. According to me, first of all, this is magnetic field. This is the current in the conductor. This will be the force on the conductor. Remember, in magnetic effect of an electric current, we studied this Fleming's left-hand rule, and we said, if you have a conductor carrying current and that conductor is placed in a magnetic field at 90 degrees to the magnetic field, then that conductor will experience a force which is perpendicular to both the magnetic field and the current. Let's see whether we've met this first condition. We have a current carrying conductor or a current in this direction and magnetic field perpendicular to it. We have achieved that. At this point, the current is to the left, and the magnetic field is into the paper. You can see that the magnetic field is perpendicular to the plane of the paper, while the current is along the plane of the paper. The magnetic field and the current, they make 90 degrees. And that means that there will be a force on that electron. How is that? Let's use Fleming's left-hand rule. This is the current, so I'm going to rotate it so that it points in that direction because it's that way. And then the magnetic field is into the paper, like that. That electron will experience a force vertically downwards, like that. And that is why there will be a force here on that electron. When it moves a short distance, that force still continues. And you can see that the force is perpendicular. At this particular point, the force is perpendicular to both the magnetic field line, which is into the paper, and the current. So again, Fleming's left-hand rule. When it moves a shorter distance, again, that force must always be perpendicular to both the magnetic field and the current. Since the force is always perpendicular to the instantaneous direction of travel of the charge, this one is very important. Since the force is always perpendicular to the instantaneous direction of travel of the charge, unlike in an electric field, then the path of that particle will be circular. Once those two conditions have been met, then the path of the particle becomes circular. Unlike in an electric field where we saw, let's go back slightly and see that. You see this curving. This curving is parabolic because the force acting on the charge is not always perpendicular to the instantaneous direction of travel of the particle. So this part, the shape of the curve here represents a parabola, while in our case here, the path is circular. So that is one of the differences between the deflection of the path of the electrons in the magnetic field and the electric field. And that is brought by the fact that in a magnetic field, the force is always perpendicular to both the direction, the instantaneous direction of travel of the particle and the magnetic field. I'm using the word instantaneous direction of travel. What does that mean? It means that at this point, at this instant of time, the direction of travel of that electron is tangential to the curve at that point. Is tangential. So once I get that tangent, I'll always get the force to be perpendicular to that tangent, and any direction which is perpendicular to the tangent on a curve will be towards the center of that particular curve. And that is why that force ends up making 90 degrees with the instantaneous direction of travel of the charge as well as with the magnetic field. The other distinction is this. You can see that the magnetic field lines are perpendicular to the direction of travel of the particle. At this point, I want to bring this idea. You will remember that in an electric field, the electric field actually does work on the charge as it moves through it, and therefore it emerges with a bigger speed here compared to the speed with which it entered the electric field. This is so because the force acting on the charge actually does work. And when work is done on an object, that object gains energy. When work is done on a charge, that charge is going to either gain electrical potential energy. In this case, it's going to increase in speed. It's going to gain kinetic energy, and therefore its speed is going to increase. This is not the case in a magnetic field. Let's go over to it and we look at the distinction. Remember, over here we said the force acting on the charge is only perpendicular to that charge at this particular point. That force is making 90 degrees to the instantaneous direction of travel. But when that charge is at a point here, you can see that the force is no longer making 90 degrees with the instantaneous direction of travel, because the direction in which it is traveling is this way and the force is this way. Notice that that force does not make 90 degrees. So that force is going to have a component in this direction, and it is that component which actually does work on the charge, increasing its kinetic energy, and hence it emerges with a higher speed. But when we are talking about the same charge moving in a magnetic field, we see that the force is always perpendicular to the instantaneous direction of travel of the particle. It's always perpendicular. That means when we get the component of that force in the direction in which the particle is traveling, that component will be zero. And therefore, that force ends up not doing work on the charge. This is very, very important. So what is the effect of that force on the charge? All it does, it is to produce a turning effect. Remember, when the force is perpendicular to the direction of travel, it will just turn the object. It's more like moment of a force about a point. So that one is a major distinction. When a charge moves in a magnetic field, the magnetic field does not do work on it, and therefore its speed remains constant. That is why the speed of that charge remains constant. And so is any other particle which is moving in a circular path. Because elsewhere in circular motion, we know that when a particle is moving in a circular path, it's evidence that there is the centripetal force acting on it, which is directed towards the center of the circular path. That centripetal force actually does not do work on that object which is moving in the circular path, because it's always perpendicular to the instantaneous direction of travel of the particle. If it were to do work, that object would continuously gain speed. But we know that this one does not happen. A good example is the gravitational pull on the Earth by the Sun. It is a centripetal force. If that force were to do work on the Earth, you'll find that the speed of the Earth around the Sun would continuously increase, but that does not happen. So it is important to appreciate that point. It's a very important point between the deflection of charged particles in electric fields and in magnetic fields. In electric fields, the electric field does work on the charge, but in a magnetic field, the magnetic field does not do work on the charge. Consequently, in an electric field, the speed of the charge increases, while in a magnetic field, the speed of the charge remains constant. We have already looked at this other distinction where the path of the charged particle in an electric field is parabolic, while here it's completely circular. So the other point we need to consider here is this. How will this particle move if we use a stronger magnetic field? And how do we strengthen that magnetic field? We strengthen the magnetic field by making sure that the current which flows through that coil is higher. If we increase the current, then we are going to increase the strength of the magnetic field. We are going to find that the force acting on the charge is going to increase. If it increases, this charge will curve more. So you're going to have a circle of smaller and smaller radius as we increase the magnetic field. That is one of the changes that we can make there. What will happen if we reverse the direction of the magnetic field? We are still there. Now this time, I'm going to reverse the magnetic field this way, keeping the current the same. You can see the direction of the force is going to be reversed, and when the direction of the force is reversed, the particle deflects in the other direction. So the curving will be in this direction if the direction of the magnetic field is reversed. Again, let's go back here and consider another situation. Suppose we were to increase the speed of these electrons. Remember how we increase the speed of the electrons? We do that by increasing the accelerating potential. So suppose we were to increase the speed of these electrons. Those faster electrons will be more difficult to curve than slow electrons. So the amount of deflection will be less. So we are going to have a circle of greater radius or larger radius or a bigger circle. Okay, again, let's go back here and consider a situation whereby this time we want a particle with the same mass as an electron, but it has a positive charge. We call such particles positrons. Suppose we were to project a positron here. It will have the same shape, but it will deflect in this direction. And finally, suppose we were to have the proton and the electron. The proton and the electron. Remember, the proton is heavy. The proton has got a positive charge, but we are going to ensure that they've got the same speed. Suppose that is the situation. What are we going to have? And this is the situation that we have. If we have a proton, number one, it will be deflected in a direction which is opposite to that of the electron. Number two, the amount of deflection of the electron is greater than the deflection of the proton. And at this point, I want to mention this. Sometimes when students see that this circle has a bigger radius, they end up thinking that this is greater deflection. No, this is less deflection. Less. Why? The amount of deflection is the amount of distance the particle moves from the horizontal line where it would have taken if this field was not there. And you can see, for example, if both particles were here, you can see that the proton just undergoes that amount of deflection. The electron undergoes this greater deflection. So the proton undergoes less deflection because it is heavier than the electron. And that is all we can say about the deflection of cathode rays in magnetic fields.